So, last time we were talking about textural properties of the catalyst and I was discussing the determination of surface area, pore volume, pore size distribution of the catalyst. So, these properties are very important when you need to characterize the catalyst after preparation. So, I was just talking about the different methods. So, one is the mercury porosimeter method, which is just based on the surface tension effect, right, and the second one is the nitrogen capillary condensation, which is based on Kelvin equation, that is vapor pressure and the pore radius, both are very important. So, if you use these two techniques, one can determine the micropores present in the catalyst, because this is here nitrogen can go inside the pores of all the catalysts. Mercury can go only in the larger pores. Under normal conditions this will not go, but if you have certain pressure in the pore, so that is related to the surface tension effect and you can determine the larger pore size here and the complete pore size distribution can be determined. So, the basic fundamental thing what is used to determine the pore volume of a catalyst. So, we are interested here in terms of the total pore volume first, then density of the pellet. So, density when I am saying, so pellet density, which is for the porous material, right. So, we represent it by rho subscripted as P, rho P, and second will be the solid density, that is the particles from which the pellet has been made. So, that is known as particle density or solid density. Right. So, we represent it by rho S. So, once these two are known, then the porosity represented sometimes by epsilon or E, right. So, which is defined as the pore volume divided by total volume. So, when I say total volume for a pellet, it is the volume of the pore plus solid volume, right. So, basically fundamentally if you know the pore volume, so pore volume is one which is generally reported in terms of centimeter cube per gram, right. So, we represent it by Vg is the pore volume. So, I will write it P dot V subscripted as this. So, that is represented by Vg, units are generally centimeter cube per gram, right. Rho P I have already defined, right. So, rho P I told you is the pellet density, right. So, 1 by rho P is basically a representation of the volume of the pellet, right. So, it means my porosity epsilon can be correlated with rho P Vg, right. This is for per gram of the solid, right. So, volume of the pore per gram of the solid divided by this density. So, multiplied by density, because 1 by rho P is your representation of total volume, correct. So, this is another definition and I can also write this same porosity based on these two densities also, that is 1 by rho P and 1 by rho S, right. So, 1 by rho P which I have written here is representation of the total volume of the solid skeletal, that is what I am saying skeletal, right, plus the volume of the pore, and if you subtract it just from 1 by rho S which is now volume of the solid, right. So, I have another equation for this is 1 by rho P minus 1 by rho S, right. So, this 1 by rho P is the volume of the pellet which includes your volume of the solid and then volume of the pore. 1 by rho S represents only the volume of the solid. So, the difference will be nothing but the pore volume and you are defining it per gram of solid. So, this is again the porosity, right. So, this is pellet porosity. So, sometimes we write it epsilon P also, right, not in the bed, right, that bed porosity will be different, right. And now similarly you can have the micropore volume. So, based on micropore volume you call it microporosity, macropore volume macroporosity, and mesopore volume based. So, mesoporosity and summation of all that can be the total porosity, right. So, these are some textural properties which are required in order to characterize the pellet. So, basically the porosity, as I said, the wider large porosity, that is because large porosity high means 0.8, it can be up to a level of 0.8, right, and very low porosity it is a kind of non porous also, right. So, that will be very highly, it has good strength, right, if it is a non porous, but as you increase. So, it means you are making a pellet more and more skeletal like this. So, these are the cavities inside a solid material, right. So, you have just like if you look at a calcium carbonate powder. So, it is a porous material, right, but if you look at a solid something like a glass. So, it may be a non porous type material. So, all these soft materials they will have kind of porosity, right. So, now determination of the pore volume. So, this is one of the most important or very common method in one way to define the pore volume and pore size and porosity, right. And if I use the nitrogen adsorption desorption method, along with this I can determine the pore size distribution also, right. So, the helium mercury method, why these two terms have been used? The reason is that helium is a light gas. So, under normal condition it can go into the small pore, it can diffuse easily into the pores of the solid, right, but mercury cannot penetrate into the pore, right, because mercury is a heavy metal, it is a normal, it is liquid, but it is a heavy metal, it cannot penetrate the pore of most of the solid under normal condition. So, how can you do that? You apply some pressure, right. So, if you apply pressure, the mercury will start penetrating, right. So, we can correlate the pressure required, right, with the radius of the capillary, because it is nothing but the principle which is here is your surface tension principle. So, which is written here, and if I just show you the slide here. So, this porosimeter principle, mercury porosimeter principle is based on surface tension forces, right. So, if you look at the structure, so basically this is a pore, a cylindrical pore. So, mercury under normal condition does not wet the surface. So, most of the surface, because it is hydrophobic in nature, right. So, most of the surface will have a structure like this when you have a mercury, right. If you just in contrast, if you have any hydrophilic material, they will have meniscus like this, right, they wet the surface, just like if you put a water drop, right, on a glass surface, it will wet, it will spread, right. But when you have a something which has high surface tension, so it will show a meniscus like this, right, because of the surface tension effect, right. So, mercury will not wet the glass surface, but water can wet the surface, and this is nothing but the wettability and wetting characteristics, right, which is related to surface tension. So, here this is what you say contact angle theta, right. So, the when you apply a pressure, because the mercury is trying to come out of the pore because of the surface tension force. So, this force is in this direction, which is your surface tension force, and that will be proportional to the whatever the length and radius. So, this term which is written here minus 2 pi r sigma cos of theta is your surface tension force, right. So, sigma is the surface tension of mercury, right. So, mercury and that contact angle theta, that will depend on the solid and the liquid property, right. So, for mercury on most of the solid surface, it is roughly 140 degree, that is the value of theta, and surface tension of mercury is roughly 450 Dn per centimeter, right. Okay. So, now what is the, you are applying pressure to penetrate the mercury into the pore, and surface tension is trying to pull it out, right. So, it means depending upon the pressure which you have applied, a definite volume of the pore will get filled, right. So, V, if I just write that volume of the mercury which has penetrated inside at a given pressure, that is correlated with the radius of that pore, right. So, the simple mathematical balance or pressure balance, if you write P into pi r square, which is written already there. So, this is the r is the radius of this capillary. So, pore radius here, right. So, P into pi r square is your pressure force and that is equal to, which is written there, minus 2 pi r sigma cos of theta, surface tension force which is opposing. So, use this, substitute the value. So, roughly we get r in nanometer unit, which is roughly 6300 divided by P, which is in atmospheric unit. There can be the slight variation in value. So, in the second one, depending upon the value of surface tension, depending upon theta value, sometimes we use 130, sometimes 135, 140. So, there may be a slight variation, but roughly the pore radius in nanometer is 6300 divided by P, where P is the applied pressure. So, you have given the pressures, right, P P plus delta P, and in that differential pressure you are calculating what is the differential volume of mercury which has been penetrated. So, that can give you the idea about the pore size distribution also, which we will talk later, but right now we are using it just to calculate the pore volume, right. So, it means this principle is used here to determine the pore volume. The reason is that now when you have any solid material, so under normal condition, when you apply pressure, this thing will happen, but under normal condition, this is actually a very specific chamber where you pass the helium first, right, and measure the volume of the helium displaced by the sample, right. So, helium will penetrate into the pore and only the volume of the solid will be displaced, right. So, it means the volume of helium displaced by the sample will be a measurement of the volume of the solid material, right, because part of the helium has gone into the pore, right. And now you evacuate the chamber, right, remove the helium and then pass the mercury, right, in the same volume of the chamber, same volume of the catalyst, same mass of that solid catalyst. So, now helium will not helium has gone inside part of the pore, but mercury cannot penetrate into the pore like what I have shown here, because you need a pressure, right, to penetrate the mercury. So, the volume of the mercury displaced by the sample is representing the total volume of the solid plus the pore, right, because it has not gone into the pore, right. So, it will displace the volume of the mercury which is outside, that is in the skeletal part of the solid as well as the pore part. So, this is a representation of the external volume of the solid as well as the that is the volume of the pore, right. So, this gives you the idea about the density of the porous material, right. So, this is representing the total volume of the solid which is a porous material, that is volume of the pore plus that, right, the solid. In the case of helium, so this is already written here, the mercury cannot pass through the pores. So, you can find out the volume of the helium displaced, which is lower number now, volume of mercury displaced will be a larger number, right. So, volume of mercury displaced minus volume of helium displaced, that is what, pore volume, right, because in the first case when you have passed the helium, helium has gone into the pore. So, it will displace less volume, only solid material density, right, and when the mercury has been passed, it cannot go into the pore, it will displace the solid as well as the pore volume, that is represented, because it cannot go into the pore. So, the mercury volume displaced is higher compared to the helium volume displaced. So, volume of mercury displaced minus volume of helium displaced is your pore volume of the solid divided by the mass of the catalyst placed. So, that is actually pore volume per gram of the solids. Okay. So, this is the first thing, and that is why I written here that volume of mercury displaced by the sample is representing the pellet density, right. Pellet density means it has porous structure, right, and volume of helium displaced is representing the solid density, because the part of the helium has gone into this pore of the catalyst and remaining is skeletal part, right. So, you can very easily find out the pore volume, that is volume of mercury displaced minus volume of helium displaced divided by the mass of the solid. So, that is your pore volume, right. And second term, which is porosity, because I have now already defined it here, 1 by rho p minus 1 by rho s, right, because the porosity is pore volume divided by total volume, right. So, most of the time when you have this kind of equation, so porosity epsilon which you are writing is pore volume. So, M p is the mass, V g is the volume, right, divided by M p V g, that is the pore volume, right, plus the volume of the solid. So, rho p V g divided by rho s V g. So, it will be 1 by rho s E n, right. This is also in the definition. So, basically what I am writing, that this is the volume of the total volume of the pore, right. This is the volume of the pore divided by the total volume of the solid. So, it should be the mass, because mass is almost same. So, M p by rho s, right, mass divided by the density. So, now this is the volume of the solid material, right, mass is same, correct. So, M p by rho s. So, you can simplify it and you will have expression what I have written earlier. So, in the form of this, right. So, you can very easily write it in terms of rho s V g divided by 1 plus rho s V g, correct. So, this is what the determination of pore volume by using the helium mercury method, right. So, you can determine the volume of the pore, you can determine the density of the solid material, you can determine the density of the porous material, right. The second thing is the pore size distribution, right. So, pore size distribution now approach is same, but that is the surface tension effect, but that because the mercury requires certain amount of pressure to allow or to diffuse into the pore of a catalyst, right. So, only up to a certain range of pressure you can do this thing. When you apply higher pressure or higher stress, the pore will get crumbled, right. So, if the material is highly porous, then this mercury porosimeter method may not work good, because it will crumble the pore, right. So, it means not all the pores or not all size of pores can be determined by using the mercury penetration method. So, only macro pore distribution can be determined by mercury penetration method or to some level of mesopores, right. The reason is that the higher pore, smaller pores will require a much higher pressure, because it is inversely proportional to pressure, right. So, if you have micro pores, the pressure requirement may be very high, right, 10,000 psi, right. So, at that time the pore may get crumbled. So, nitrogen adsorption desorption principle is used to determine those pores. So, that is based on Kelvin equation, which is related to vapor pressure, right, required to fill the pore, and then it dissolves from the pore. So, that we will discuss later, but this mercury porosimeter or pore size distribution determination, which is an important property of the catalyst. So, it is nothing but the distribution of pore across the inner and outer surface, that is we are interested in micropores, macropores and mesopores, right. So, the most widely used method for determining the pore size distribution in solid is mercury porosimeter method. So, surface area is determined by the BET method, but the pore size distribution, when I mean to say pore size distribution, I am interested something like the volume, suppose if I write here, or delta volume, right. So, I will write it first this, sometime we write it dV upon dA also, that is A is the radius or dr if I write. So, right. So, dV over dA, which is nothing but we are trying to find out delta V upon delta R or delta of A, right. Here we put the just radius or small a or r, right. So, it means the distribution of the pore, when I say, it may go like this, right. The pores may be of wide size, that is volume versus radius. If I am calculating, the same thing can be plotted in terms of pressure also, because this dV you are calculating from differential pressure, right. So, I am interested in determining these kind of distribution. So, this can be a just like a narrow pore size distribution, right. That is when you have only a definite size of the pores are available in your catalyst, but if you have micropore, mesopore, so this value can be say 1000 angstrom here, right. This can be just at 2 angstrom or 10 angstrom here. So, you can have a wide distribution in a catalyst, right, and that you get when you sinter a catalyst, when you age a catalyst, when you decide the slide size. So, you can have a wider pore size distribution also, but most of this we like to have a narrower pore size distribution, we want to make it more selective or more specific in its action. So, the mercury porosimeter, the principle which I have just talked, the pore size distribution can be determined by measuring the volume of mercury that enters the pore under a given pressure, right. So, this is based on surface tension effect, right. So, this is your pressure, here it is 2 pi sigma cos alpha or theta, right, whatever, and divide by R p, which is radius of the pore, same thing, right. 6300 divide by the pressure, where that gave you the radius in nanometer unit. So, depending upon the value of sigma in a specific unit, right, you will have the different this radius units, right, and pressure unit can be in psi, it can be in Newton per meter square also. So, sigma is the surface tension, right, it has different values. So, as I said 480 Dn per centimeter or 450 Dn per centimeter. So, it can have different units, you can write that, and pressures, the range which we give, it can be 0.1 to 200 megapascal, right. This allow the pore size which may be in the range, you can very easily calculate here, right. You know the value of pressure, suppose you give this pressure or you give you apply give this pressure 0.1 megapascal, right, 1 megapascal is 10 atmosphere, right, or 100 atmosphere. So, you can very easily find out that, right, and different conditions you can have that, right. So, this 200 megapascal, the because this is very high pressure, that time the radius will be very small, right. So, you can very easily calculate that. So, this I have already discussed, that is the related to the surface tension effect. So, pressure required to penetrate the mercury into the pore is equal to surface tension force. So, you can calculate the pore size distribution, and either of these equations can be used and you can find out the pore size distribution. So, this is one method, right, to determine. So, basically what we have to do, we have to make a differential or cumulative analysis type, right. So, when we use this mercury penetration method, so at different conditions of pressure, we calculate the volume penetrated by the mercury, that is what delta V I have written, right. So, now this delta V between two pressure differentials, right, P and P plus delta P, you can calculate what is the volume of mercury which has been penetrated into the pore, right, and that volume is related to the radius of that, right. So, you can very easily calculate the pore volume, because pi r square into L, that is a kind of length, right, if I have, that is the pore volume, right. So, if I have n number of pores and r is the radius of that pore, L is length. So, I can very easily find out the pore volume of that, right, and that is what the calculation which you have done there in your this helium mercury method. So, total pore volume of the solid is determined, right, and I am calculating the fraction of the pores which has occupied the volume between V and V plus delta V, right, at a given pressure of P to P plus delta P. So, when you are increasing the pressure, the pores are getting filled. So, in a differential pressure, what volume fraction of the pore has been filled, and that volume fraction is related to the radius because of the surface tension equation which you already calculated. So, I can correlate that volume with the radius. So, now I am writing the cumulative curve in the form of, so if I have a cumulative plot, so that will relate your pore size distribution. So, volume of the pores getting filled versus pressure, if you look at here, and which is related to your or radius, I can say pore radius A or R, right. So, this cumulative pore size distribution will go like this, right. So, this is indicating that the pores are totally filled here. So, basically this will be your Vg here, right, the volume of the total volume of the pore, but I will say because it is a mercury penetration method. So, this will include only the macro pore volume or pores of certain radius up to which the pressure has been applied, whatever it can be your 5000 or it can be your 500 something whatever in the unit say 5000 psi. So, this can be of that order, right. So, you can very easily calculate this and then you can determine the total value, right. So, I can have the idea that starting from a pressure which is atmosphere here 1 atmosphere 14.7 psi here, right, and then you have calculated a differential volumes. So, I can very easily find out between these two pressures what is the radii here A and A plus. So, this basically this side when I am going this radius is smaller, right. So, because here this is the smallest pore. So, my radius is increasing in this side pore radius, right. So, this is the smallest pore which is getting filled and this is the largest pore here. So, basically this is A and this is A plus delta A. So, I can have a relationship for delta V upon delta A, that is change in radius or change in volume per unit radius, right, dV upon d log A sometime we put, because the number is very very small. So, we just try to look at in a integral form, right. So, on a larger scale. So, we can very easily plot this in the form of delta V upon delta of radius, right, and then plot it versus P or radius. So, that will become a cumulative pore size distribution. So, this is your cumulative pore size distribution and from this you can find out the pore size distribution, that is dV over d of log A, what I was saying, something like this. So, this can be a graph of delta V upon delta A or delta of log of A. So, this one is your pore size distribution, whereas this is a cumulative plot of that. In this case, this nitrogen adsorption desorption method, the principle is different because this is based on the vapor pressure or Kelvin equation, right. So, this is your Kelvin equation which relates the vapor pressure required to fill a pore as a function of radius, right. So, at a given condition what volume of the gas is penetrating or entering into the surface. So, the pores are getting filled accordingly, because the pores may be of different shape and size, right. So, this nitrogen adsorption desorption method can give you the idea about the pore geometry also, right, because the pores it may be larger, it may be smaller, it may have a ink bottle shape also, right. So, there will be a kind of adsorbed layer thickness and then the desorption starts. So, first the gas adsorbs and when it all the pores are filled and when you release the pressure. So, the pores will start desorbing, right. So, largest pore will empty it first and smaller pores will empty it at a later stage, right, when you are releasing the pressure, right, because the Kelvin equation which relates the vapor pressure, right, required to fill a pore, right, and then there will be a kind of adsorbed layer thickness. Generally, if you look at this Kelvin effect, so you have this pore. So, there is a kind of adsorption here. So, there will be a thickness of that adsorbed layer, right. So, actually the vaporization takes place from this radius, whereas the actual pore radius is this, right. So, if I talk this is the diameter. So, this is my A actual pore radius from here to here, right. But when you have done this nitrogen adsorption or nitrogen adsorption desorption method, then you are getting, because this is an adsorbed layer, this will not desorb at that time, right. The Kelvin effect is only from this point where the pores are filled, not adsorbed, right. So, this if I talk this, that is related to your adsorbed layer thickness, which I say delta thickness of the adsorbed layer, right. So, my Kelvin equation is talking about this radius which may be your r, right, but actual thickness, actual pore size or pore radius is A, which is r plus delta, right. So, when you use this equation, you have to use a different empirical correlation to calculate the thickness of the adsorb layer, and that can be determined by using the T plots, right. There are different methods, we will talk on that, but one can find out this adsorb layer thickness, which is based on the empirical correlation, but the funda is related to your Kelvin equation, right. So, some saturation, what is the saturation pressure, what is the pressure, and then one can very easily calculate for nitrogen, because the all the nitrogen has the property not like the mercury, which is trying to oppose, right. It can wet the surface of most of the pores, right. So, adsorb that means the adsorption is possible. So, that is why there is an adsorb layer thickness, right, and then this is the radius of the capillary. So, capillary condensation phenomenon is for this radius. So, your Kelvin equation this R is talking this, not this A, right. So, whatever R you get from Kelvin equation, you add delta to that, and that will be your actual pore size, actual pore radius, right. So, this is what we need to calculate when we use this nitrogen adsorption desorption method, and since the property of the pore will depend, or this R and delta will depend on the type of pore, ink bottle effect what I said, right, adsorption hysteresis. So, now what I am saying that what is the adsorption, basically the it is a surface phenomena which I said, and you get the different temperature or at constant temperature when I say isotherm. So, at one temperature you are looking the effect of pressure, right. So, that is known as adsorption isotherm. So, here generally in this case adsorption we are looking something that the molecules which comes to the surface, they will get adsorbed first, and now you are increasing the pressure, right. So, when the further increasing the pressure, so this is the adsorb layer, and then the condensation takes place, right. So, smaller pores will get filled first, and gradually it will go into the larger pore. So, when it reaches to the saturation, all the pores are filled with nitrogen, right, and now you start desorption to release the pressure. So, when the pressure is released, then the vapor pressure will get lower and lower, right, and the pores will get emptied, right. So, we are calculating the volume of the nitrogen desorbed as a function of the pressure, right, and in each differential intervals, that is the release of pressure from highest pressure to some pressure delta p, p minus delta p, and so on p minus 2 delta p, and you are just measuring this volume of the gas which is desorbed, right, and that volume is related to the radius of this capillary, and to that radius you calculate this delta and add, and you will have the total pore size distribution or for different. So, this can give you the micropore, because capillary phenomenon is only applicable in small pores, right, not in the wider pores. So, that is why the mercury penetration method works only for the larger pores, and nitrogen adsorption desorption method works for the smaller pores, right. So, by relating the relative pressure and the pore radius, the pore size distribution of the catalyst can be determined, but only for the micro pores, right, less than 20 nanometer, right. So, this is written here that this BET method can be used to determine the pore size distribution. So, generally the surface area BET is generally used for the surface area determination, right, but then we are using this for pore size distribution, your BJ's plots with the Barrett, Joyner and Hollanda isotherms, right. So, you can determine the pore size distribution, which is basically on the nitrogen adsorption desorption phenomena, right. So, this is just what I said, that less than 20 nanometer or 200 angstrom except at high relative pressures, right. So, that is required because we are condensing the nitrogen on the capillaries, right. So, capillary condensation, this is known as Kelvin equation. So, ln of P by P0, where P0 is the saturation pressure, sigma is the surface tension, right, for nitrogen, V is the volume of the gas adsorbed, theta is the contact angle. So, generally we take it 0, because nitrogen generally wets off all this surface, right, liquid nitrogen I am talking, right, and R is the gas constant and T is the temperature in Kelvin. So, this is what the T method what I was talking, that is generally used. So, BET is only valid for small pressure intervals. So, we have to give a differential pressures which is of smaller order. So, that the pores, because you are talking of micro pores here, right, between say 10 to 20 nanometers, right, what we are talking. So, those kind of pores we are talking here, right, and sometime we go up to the 50 or 70 nanometers. So, but the results may not be very good, because the Kelvin equation is valid only for the capillary, it is a capillary condensation phenomena, right. So, small pressure intervals, and interpretation is not very easy, because delta is also related here, and the pressure differential which you are calculating, and corresponding to that the volume of the gas which is dissolved, that is important, right. At different condition you are measuring the volume of the gas adsorbed. So, again we can have a cumulative plot like what we discussed for the case of mercury penetration method. So, thickness of the adsorbed layer, which I am writing here delta. So, sometimes we call it T also, right. So, adsorbed layer thickness T plots, right. So, that can be determined. So, this is what we are talking, a monolayer thickness of the adsorbed layer. So, that is roughly this is related to this only, but empirical correlations are available for the calculation of this delta thickness of the adsorbed layer, which is nothing but calculated from the same equation. That time we calculate this R and taken to other side, but there are empirical correlations for calculating this thickness of adsorbed layers, right. So, this we will talk later, because this is the T plot which is generally used to get this information, and finally, a pore size distribution. So, this there is always a kind of hysteresis here, that is what adsorption desorption hysteresis, right, and that hysteresis gives you the idea about the microporosity and the shape of the pores, right, ink bottle effect what I was talking. So, this gap which I am talking, right. So, when the pore size distribution is wide, right, then this gap will be more and more, right, or when there are some, suppose you have alumina type pellet, you may not get this kind of effects, right, but when you have a kind of structure which is complex, see, there are micropores and the pores are irregular in shape, zigzag type or ink bottle effect. So, this phenomenon is because of the ink bottle effect, because it is nothing but, as I said, the condensation and then vaporization. When you are applying the pressure, the nitrogen gas is being adsorbed on the surface, and when you release the pressure, it dissolves, right. So, but principle which is we defines here A and A plus delta A, that is the volume of the gas which is dissolved at a given pressure differential, right. So, this adsorption desorption kind of hysteresis, because the pores may not vacate completely at that time when you apply release the pressure, right. So, a higher pressure may be required to higher pressure release may be required to vacate all the pores, right, and that is known as hysteresis. So, generally when you have a single kind of distribution or simple pore, single one side pore distribution, then this kind of hysteresis may not arrive, right. But when the pore complex geometry is very complex, then the hysteresis will be more and more. So, this is basically the moles which are dissolved or adsorbed as a function of P by P 0, that is a till saturation, right. So, adsorption curves goes like this, right, because it is related to the pressure, and when you release, then your moles will dissolve like this, right. So, here you can see at this, when you look at the desorption pressure, the number of moles which have been released from the surface, they appear to be higher, right, because of the ink bottle effect or hysteresis. So, adsorption isotherm, as I said, that is basically what we are talking at constant temperature, we try to study the effect of pressure, right. So, plot of amount of gas adsorbed as a function of pressure versus pressure at constant temperature is known as adsorption isotherm, right. The other side, if you plot adsorption or moles adsorbed, right, as a function of temperature at constant pressure, that is isobar. So, generally in most of the heterogeneous catalysis or solid, when the gas is adsorbing, it is more a pressure phenomena, because it is something which is related to the sticking probability, right, and that is related to the pressure, right, less on temperature, right. So, we generally talk in terms of the isotherms. At one temperature, we calculate the molecules which adsorb on the surface at different pressure, right. So, you can see here that the behavior may be different, right, depending upon the type of solid property or depending upon the behavior of the gas, because it is depending on the type of the gas, it depends on the type of the solid surface, and its textural property, right. So, the pressure versus this P by P 0 what is written here is basically P 0 is the saturation pressure, right. So, and P is the applied pressure. So, P by P 0 is just representing this, that what I say here, if you look at here, this is the first type 1 adsorption isotherm, which just indicates that once the saturation appears or when the pressure is saturated, no molecule can further adsorb on this surface, almost constant, right. So, this cannot be a physical adsorption, because I said that physical adsorption is basically the condensation of the molecule, right. So, when you have the molecules and you apply the pressure, the more molecule will come and sit, right. The water, if you apply pressure, more and more water will get condensed, right, on the surface. So, but this kind of phenomenon is very specific. So, it means once the saturation has arrived, then molecules are not adsorbing further. So, it is something like a chemisorption, right. When you say that active sites are available and a gas is adsorbs on that surface, right, or adsorbing on that surface. So, that time this may be effective or this may be considered, right. So, that is known as just like a type 1 adsorption, which is known as Langmuir adsorption, right. Basically, we say that the adsorption is related to pressure and the concentration of the vacant site, right. So, once the vacant sites are not available, the adsorption is not possible. So, that is what the indication here. Whereas, this if you look at here, right. So, this type 2nd adsorption, it shows that some saturation which you are seeing here now has appeared here, something like this, right. So, this could be a monolayer here in this, but continuously further adsorption is possible, right. Adsorption is possible. So, this is a phenomenon of multi-layer physical adsorption. So, one layer has formed, right, and but there can be the subsequent adsorption, right. So, you are not getting any kind of hysteresis in these, right. So, type 1, type 2nd, so physical adsorption or chemisorption here, but monolayer coverage, this is multi-layer coverage, and here again it is a kind of multi-layer coverage, right. But this kind of behavior you can see here is generally possible only in the very rare substances or when the material has very low porosity, microporous materials, right. Then you can see this kind of behavior, that you are applying, right, the pressure, and then at higher pressure, very high pressure only the pores can get filled, right. So, but these are rare, and here you can see the adsorption hysteresis, right, that is the adsorption desorption because of the complex pore geometry. So, pore geometry may be microporous, macroporous, and the ink bottle effect what I said, the pores are narrower and wider at some other ends, right. They are very tortuous in path. So, these kind of behaviors are very rare, right. This one is again a very rare behavior, but it represents a similar to this, right. So, there can, what I mean to say, depending upon the type of solid and the gas, the adsorption phenomenon may be different or depends on the type of solid and their physicochemical property. So, this is what the type 1 adsorption which I was talking, a Langmuir adsorption, right. So, that is related to your monolayer coverage. So, once the monolayer is formed, no further adsorption, and this phenomenon can be used to determine the monolayer coverage, right. So, basically the total surface area of the solid material which contains the active sites, right. So, when you have a chemically active gas, it will adsorb only on those surfaces where the active sites are available. So, this can be used to determine the surface area of the active metal, right. But if you have the physical adsorption, then here the value may not be correct, right, because this will report a larger value, right. So, this equation which is written, and later on we will use it to determine the kinetics also. The basically we are saying that rate of adsorption right is related to some kind of sticking probability. So, this is proportional to whatever the fraction of the sites which are vacant like this theta, right, and the pressure of the gas, right. So, 1 minus theta when I am saying, so theta is the fraction of the sites which are already covered. So, 1 minus theta is the fraction of site which are available. So, you can write sometimes in terms of C V times the pressure also, right, where C V is the concentration of the vacant site, right, and desorption, because desorption takes place only from the sites which are already covered, nothing else, right. So, desorption is proportional to the fraction of the sites which is covered, right. So, you can put some constants here. So, sometime we call here is sticking probability. So, K 1 times 1 minus theta times the pressure, right, and this is related to only the concentration of the vacant site. So, K 2 times I can write here K 2 times theta, right, and when the system, because whenever you are talking the equilibrium, then rate of adsorption will be equal to rate of desorption. So, it means at equilibrium your rate of adsorption is equal to rate of desorption. So, you will have simply K 1 times 1 minus theta times the pressure of the gas is equal to K 2 times theta, right, and this K 1 by K 2 is your adsorption equilibrium constant, capital K, right. So, you can very easily write this theta which is written here, right, K p over 1 plus K p, right. So, if you just do this, so your theta from this theta over 1 minus theta is equal to K 1 by K 2 times p. So, I am writing it capital K times p, right, and you solve this for theta. So, theta becomes K p divided by 1 plus K p, where capital K is your K 1 by K 2 adsorption equilibrium constant, right. So, this is a chemisorption type thing, chemical reaction, chemically adsorbing the gas, and that is why we use this equation for determination of kinetics of adsorption, right, and later on we will call it Langmuir model or Langmuir isotherm or Langmuir based rate expression for heterogeneous catalytic reaction, right. So, the funda is that at equilibrium the rate of adsorption is equal to rate of desorption. The adsorption rate is proportional to the partial pressure of the gas, right. So, there may be a series of the gases, right, and so it will depend on all those partial pressures, right, which are effective coming and that. So, K 1 is kind of that temperature effective, right, and depending on the sticking coefficient or probability of the gas to adsorb on the surface, right. So, this equation is very important and we will use it throughout the course, right. So, N adsorption which is written in terms of the fraction of the surface covered. So, sometime theta I have told earlier also that theta can be written in terms of V by V m, right, where V m is the volume of monolayer coverage, right. So, this is nothing but V m volume of monolayer. So, monolayer coverage, right. So, this basically this is the volume of the gas which is adsorbed at any pressure, it will increase, but when it reaches to V m, so there will not be any adsorption. So, this is basically the number of molecules which are adsorbed here at V m, right, the surface is covered and at that condition. So, there is a maximum number of molecules of the gas adsorbed when a monolayer forms, right. So, we will talk on that later also, but there are certain assumptions of Langmuir adsorption isotherm, because it represents a kind of chemisorption, it is not valid for physical adsorption, right. So, it says that the surface is homogeneous, whereas the surface cannot be homogeneous, right. You are talking heterogeneous catalysis reaction, the surface is heterogeneous, right. There are active centers, right, and at some of the locations there are no active centers, active sites, right. So, it says that the Langmuir isotherm says that the surface is homogeneous. So, it means the adsorption sites are energetically uniform, right. It means the adsorption will take place at all locations at the same rate, which is not right, correct. The monolayer adsorption, we are talking that once a monolayer forms, there will not be any further adsorption, that is the derivation. This is also not correct in all cases, right. So, there are certain modification required, which we will see later, and there is no interaction between the adsorbed molecules. So, actually it says that heat of adsorption is independent of surface coverage, because when the molecules are adsorbing, right, the phenomenon is exothermic. So, heat will release, right. Now, when you are looking the adsorption on a bare surface, so a solid surface the gas is coming, and when that surface is covered, the gas molecule may come and again sit over that, right. So, multilayer coverage when we are talking. So, the heat of adsorption will be different, right, and but it says that whether it is a bare surface or a fresh surface or covered surface, then heat of adsorption in all cases will remain same, which is not right. So, generally the heat of adsorption decrease with surface coverage, right. So, the other isotherms has or isotherms have taken care of that, right. So, type 2, type 4 which I was talking. So, type 2 is a BET type isotherm. So, it talks on multilayer physical adsorption. So, it starts from this point, right, and this is common for many porous materials. So, when you have physical adsorption like BET isotherm we are talking. So, the isotherm takes care of this. So, Langmuir isotherm says that when this forms B has arrived point, no further adsorption will take place, but in the case of BET isotherm, the adsorption may be possible and heat of adsorption may vary with surface coverage, right. So, this point which is said here, the surface is energetically uniform, has been taken care by second isotherm, which is known as BET isotherm, right. This type 4, again as I said here the hysteresis is there, right. So, it means the condensation is taking place at higher pressure, right. What I said, especially in the smaller pores, capillary condensation phenomenon, right. Otherwise, the other things are same. If you look at this is just like this curve, right, this type, but here the desorption has started, right, or condensation has started. So, this is similar to type 2 at low pressure, but the pore condensation starts at high pressure. The pores gets filled, rather adsorbing, right. Whereas, type 3 it talks on strong cohesion force between adsorbed molecules, right. So, when the molecules are adsorbed on the surface, there is a kind of cohesion. So, it is similar to the BET type 2, but the only thing that the molecules there are certain kind of forces, certain kind of force between the similar kind of molecules, right, because the molecules are already adsorbed on the surface, right, and when they are adsorbed there will be a kind of force. So, the adsorption energy or the probability sticking what you say, right, that will change when the coverage is already there, right. So, that has been taken care in this isotherm, and this is but says that there is a strong cohesion force between the adsorbed molecule, something like say water which adsorbs on the hydrophilic activated carbon. So, you will have this kind of isotherm, right, similar to the BET isotherm. Whereas, type if you third, right, 4 is similar to third, right, at low pressure. So, this is similar if you look at here, but again the pore condensation phenomenon at high pressure, right. So, this is the what you see here condensation phenomena, hysteresis kind of hysteresis, right. So, otherwise this isotherm and this isotherm same. So, generally these kind of isotherm 3rd, 4, 5 they are rare, right, and only available when the material is microporous with irregularity in the pores, right. So, microporous and irregular pores. The hysteresis is always there when you look at the adsorption desorption phenomena, right. So, Langmuir isotherm when you are doing. So, this is just like a zeolite catalyst there if you look at here, right, which is nothing but the silica alumina material and having a channel type structure, right, like a crystalline channel structure. So, here the strong adsorption at low pressure you can see here that due to the condensation of the in the micropore, because zeolites have mainly the smaller pore size, right, mesoporous materials, right. So, because in this type of material the capillary condensation phenomenon is common, right, and this condensation phenomenon shows this kind of hysteresis, right. And at higher pressure, if you look at the saturation due to finite pore volume, because that time when the higher pressure, though almost the pores are saturated, right, but there are again the micropores. So, here the condensation within the zone and but at very high pressure. So, these type of isotherm are valid or available or can be seen only in a very small pore size, say 10 angstrom pores, right. So, microporous material not even the mesoporous material. So, we will talk on that later also. So, determination of surface area, that is very important. As I said, the BT isotherm is generally used for determination of surface area of the solid material. So, then we look at the gas, type of gas. So, generally as I said, nitrogen, argon, carbon dioxide, krypton, any gas can be used, oxygen can also be used, right, as an adsorbate gas for determination of surface area. It will be related to their boiling point, because the condensation, right, it is a kind of condensation phenomena. You have to put the bath of that temperature, cryogenic conditions are to be created in order to allow the gas molecule to adsorb on the surface, right. So, this is just the liquid nitrogen, say at 77 Kelvin, argon 87 Kelvin, carbon dioxide requires 194 Kelvin. So, high temperature, and krypton is 120 Kelvin roughly, and area per molecule is also equally important, nanometer square, right, per molecule. The idea is that when you determine the surface area of a catalyst, the molecules gets adsorbed on this surface like this. So, I am talking a porous structure, and on that there is a adsorption of the molecule, physical adsorption of the gas molecule. So, you get a curve when you look at the adsorption phenomena, your curve will be something like this, whatever, right. So, what we are looking at this, when the monolayer forms, we are calculating this VM, volume of the monolayer coverage, right, and to cover this or to form this monolayer, how many molecules of that gas. So, this is the molecule of the gas, which may not be completely spherical, a projected area we need to consider, right. So, this and when the monolayer is formed, we are assuming that this layer has been covered by these molecules, right. So, we are calculating this surface area, actually we need to calculate this surface area, but this surface area is related to the number of molecules, because we are saying that the monolayer has formed, right. So, we can use the principle of the molecular area of the gas for the determination of surface area, right. So, I stop here and we will continue it next time.